Alright, in this video, I'm just going to give a quick rundown on what Gauss's law is, and then just do some simple examples. So basically, Gauss's law states that electric flux is equal to the surface integral of electric field dotted with dA. And that, in turn, is equal to charge enclosed over epsilon naught. So charge enclosed is basically just how much charge is being enclosed by this Gaussian shape. Now we have two shapes we're going to talk about. We're going to talk about a sphere and a cylinder. So for the sphere, basically we just say, okay, we're going to follow Gauss's law. E dot dA equals QEnC over epsilon naught. Epsilon naught is just some random constant. It's the permittivity of free space. Doesn't really even matter. So the surface integral thing looks kind of scary, but really all you do is you just say, okay, we're only dealing with a simple shape, so we can just say the magnitude of electric field times the surface area of a sphere. So the surface area of a sphere is just 4 pi r squared, and that's still equal to QEnC over epsilon naught. So then we can just say that the magnitude of electric field equals QEnC over 4 pi r squared epsilon naught. Okay? That is always true for a sphere. Now, the other case we have is a cylinder. So really it's the same exact thing. Surface integral of E dotted with dA equals QEnC over epsilon naught. Now we say, okay, magnitude of electric field times the surface area of a cylinder. Now, okay, here's the cylinder. And basically, we're only talking about the lengthwise surface. We are ignoring the faces. So yeah, the faces have surface area, but we are ignoring them. So in that case, you would say, okay, the surface area would be the perimeter of a circle times the length of the cylinder. So you'd say, okay, that's simply 2 pi r circle times L. And that is equal to QEnC over epsilon naught. So then we're just like, okay, electric field equals charge enclosed over 2 pi RL epsilon naught. And that is the formula you can always use for a cylinder. So now let's just do some quick examples. Let's say you're given a sphere, and here's the sphere. Okay. And let's just say it's a solid sphere, and it has a volumetric charge density of rho. So rho has units of coulombs per meters cubed. Basically, it represents the total charge divided by the volume. So this will be important for when we try to figure out this epsilon naught in the formula. Or not the epsilon naught, the charge enclosed. So let's say we needed to find the electric field present inside this sphere. We'd say, okay, it's a sphere, so we can just use our sphere formula, and we would just say, okay, E equals charge enclosed over 4 pi r squared epsilon naught. So now this r right here, that is the radius of what's called the Gaussian sphere. So basically we're imagining an imaginary sphere that's basically saying, okay, a sphere from any radius from 0 to whatever the heck this radius is represents the Gaussian sphere. So it's just the instantaneous radius of the Gaussian sphere. So now for this case, if we want the radius, or if we want to find the electric field on the interval where 0 is less than r, we would say, okay, E equals charge enclosed. Now, what is our charge enclosed? In this interval, we are going to enclose a charge that is equal to the charge density times the volume that we're enclosing. So you just multiply this row times the volume. Now the volume of the Gaussian sphere at any radius would be the volume of a sphere 4/3 pi instantaneous radius of the sphere cubed. Then this is our Q, E, and C. We can simply plug that into the formula, and we'll be left with pi, or rho 4/3 pi r cubed over 4 pi r squared epsilon naught. And then we can simplify this and just say E vector equals 4 rho, the pi's cancel out, r over 3 epsilon naught r hat. And now this would be the electric field, an equation for the electric field at any radius of Gaussian sphere. Okay. Now another scenario is, let's say we have a cylinder. And this cylinder is a conductor. Now, here the shape doesn't really matter, but another thing you need to know is the electric field inside a conductor equals 0. And that will always be true. So if you're ever finding the electric field inside a material that's a conductor, it's always going to be 0. And yeah, that's pretty much it. Do some more complicated examples in some other videos.